Hi, thank you for choosing this video. I'm Dario, and in the next minutes I will present you the main results of our research. We focused on an underexplored area of deep learning, in between theory and practice. In fact, our work is concerned with empirical measurements of quantitative theories about deep networks behavior. Before delving into the main details, let me clarify why we did choose this line of investigation. There are currently two lines of research aimed at understanding deep learning. From one side, we have theoretical works on relations of infinite width networks with the neural tangent kernel, which are able to prove convergence theorems. However, they don't have a real impact on the practice because they lack actionable results on realistic networks. On the other hand, we have large-scale experiments that train multiple variations of common architectures to find the better performing hyperparameters and to get the best performance. Unfortunately, the complex interdependence of network hyperparameters renders it impossible to map the whole parameter space, and the obtained results usually lack universal validity. It gets worse. These experiments are typically non-replicable due to the huge computational budgets used. So, we choose to mix both approaches to get the best of both worlds. In our work, we gather quantitative theories that hold on very wide networks, and we measure if they also hold on realistic models. In doing so, we highlight some discrepancies between the theories and what actually happens in the deployed model. We think that this mixed approach can give a fast feedback to theoretical development and can help in better understanding deep learning models. In this work, we focused on the Polyak-Lozhaziewicz condition since multiple quantitative results related to convergence, conditioning, and generalization are known for this class of functions. Moreover, this condition has been recently used in theoretical works on wide networks and has thus proved its usefulness in deep network analysis. The next parts of this presentation are structured as follows. First, I will briefly introduce the main properties of PL functions and their conditioning theory. Then, we will discuss some surprising experimental results, which partially contradict the available theories and thus deserve more attention, as they are a step in our understanding of deep network models. In the last part, I will talk more about possible consequences of this line of research and present future research directions. So, let's begin. First, the definition of the PL condition. Given a function h from a set x to R, we define h star as its infimum over the set, and we say that h is mu PL if this equation holds for all x. The equation essentially means that we can bound the optimality gap h of x minus h star at a certain point using the norm of the gradient of the function at the same point. This has multiple consequences. First, all local minima of PL functions are global. In fact, it is easy to see that for stationary points, the optimality gap is zero, as it also happens in convex functions. However, in this case, uniqueness of the minima is not guaranteed. An interesting thing to notice is that the PL condition is a generalization of convexity, as strongly convex functions are also PL, and this leads us to ask if PL functions are as easily optimizable as convex ones. Fortunately, the answer is positive, and they enjoy exponential convergence to the minima with many common first-order optimization methods. Assuming L smoothness of the objectives, in fact, the following formula is valid under gradient descent. We can see how the optimality gap shrinks by the factor 1 minus mu over L at each step. This allows PL objectives to provide convergence guarantees. Moreover, for overparameterized networks, we can assume that h star is zero, as they are able to completely overfit the training data, and this will enable us to provide estimates on the network progression and measure how accurate they are. The last interesting property for these objectives is that generalization estimates based on stability have been obtained, and the comparison of these with the tested performance of trained models will allow us to assess their efficacy. Let us now turn to the other theoretical part of the work, concerning the conditioning theory for PL functions. We start by casting deep learning as an optimization problem. In the classical supervised learning setting, we are given n examples xi, yi, sampled independently from the same unknown distribution D. We are also given a loss function L, typically convex, and a parametric estimation function f, realized as a neural network model in our case. We can then define big F from the space of parameters theta as the network evaluation at all examples, and realize that the network objective can be defined as the composition between L and big F. Given their importance in the convergence speed, we are interested in the PL and smoothness constant for H that we have previously named mu and L. In order to do so, we have first to define two matrices, K and G. K is the finite neural tangent kernel of the analyzed network, while G is the kernel matrix when we use F as a feature extractor, and which is relevant when only the last layer of the network is trained. It turns out that mu and L are proportional respectively to the minimum and maximum eigenvalue of K when we train all layers, and to the eigenvalues of G when only the last layer is trained. Moreover, the conditioning kappa of K and G decreases exponentially in depth for infinite width networks, and it is related to the PL convergence speed. After this brief introduction of the underlying theory, we will now discuss the major experimental findings about conditioning, both at the initialization and during training, convergence speed, and generalization of networks. We will present graphs referring to overparameterized fully connected networks with ReLU nonlinearities, which we have trained under cross-entropy laws on Cypher10, as the other settings we have tried resulted in similar graphs. We start with our results on the log conditioning at the initialization of the G matrix for 500 examples at different width and normalization setups. In particular, we notice how conditioning in both normalization settings decreases exponentially until a certain layer. After that, the conditioning for renormalized network decreases more slowly, while that of non-renormalized network increases slightly. Moreover, this effect is less visible the wider the considered networks are. This proves that conditioning behaves differently between the two settings, contrary to the current theory, which uses the central limit theorem and thus implicitly assumes infinite width networks. Moreover, this hints at the fact that normalization in earlier layers shouldn't have a big effect on the trainability of networks, while it certainly does in later ones. But what happens to conditioning during training? In the image, we can see its progression for different layers and under different learning rates. We can see that for smaller learning rates, conditioning increases very slowly during the whole training, while for higher ones, it initially spikes, but then keeps reducing during the training trajectory, even ending up better than at the start of the optimization. This runs contrary to the way convergence theorems on wide networks are proved. In fact, it is usually assumed that conditioning worsens during training in a way that is proportional to the distance of the current weights from the initial ones. The obtained estimates are much more pessimistic than what we can see in this picture. We think that this aspect of conditioning needs more studies, as a good understanding of this phenomenon could give stronger guarantees on the convergence of medium-sized networks. We now turn to the prediction of the loss decrease at the next optimization step. In the figure, we have plotted the ratio between the predicted loss value at the next step and the actual loss. As you can see, the predictions are fairly accurate at later epochs, but much less so at the start of the optimization. This has possible applications in mechanisms for model selection, as we are able to accurately predict a network loss value at later epochs after just a few epochs of training. However, we highlight the need for more research in this area, aimed at providing more accurate loss decrease predictions also in the initial epochs. This effect would allow a more useful model selection procedure just from some measurement at initialization and could have applications to neural architecture search. As our last graph, we present the obtained bounds on the generalization gap for different number of examples and during training. The bounds improve with larger PL coefficients mu and with increasing optimization, or with a smaller Lipschitz constant of the network objective, but they remain nonetheless vacuous for the whole optimization trajectory in the considered setting. This highlights the need to find more realistic bounds on generalization that are able to describe what happens in realistic networks. Let us conclude with a few key takeaway points. We have shown how measurable theories about networks can give us more information about network optimization and what kind of interesting applications stronger theories would ensure. The main experimental findings that we have uncovered are first, the difference in conditioning between the two normalization settings in networks, which runs contrary to the available conditioning theory on wide networks. Second, the fact that conditioning worsens much more slowly than the available pessimistic estimates. Third, we can predict loss decrease after a few epochs of training, while we have rather estimates at the beginning. And fourth, the fact that the current generalization bounds are vacuous. Given these findings, we think that the most promising future research directions are to consider finite width effect in conditioning theory, to investigate the reasons behind the slow worsening of conditioning, to find other methods to better predict the loss decrease, and to extend the exposed analysis to other architectures like CNN, ResNets, and transformers, which is a fundamental step in enlarging the impact of the exposed techniques. So, thank you very much for following the whole presentation. I hope I convinced you that an empirical approach backed by theory is an underexplored research area which can help us better understand how neural networks behave and can have wide applicability in speeding up the training process and the model selection procedures. If you'd like to have more details, please scan the QR code on screen to reach the paper material. And if you are interested in knowing more about our research, be sure to visit us at the poster section to have a talk.